to review our ideas about polynomous logistic regression. We have a lot of choices of models, as opposed to some of the other situations that we've seen here. And there are certainly popular ones, but of course, as always, your choice of model should depend on your hypothesis and the structure of the data, and what you think, what it is that you want to measure. And let's recall that there's the first class of models we looked at were these ones that I said were like partition models. And you want to think about this as a sequence of partitions that are nested. Binary models. The example, which I'll return to for the other ones, just so we can orient ourselves, is this cancer radiation exposure example. There isn't even data to worry about. Let's say this is a radiation predictor or whatever other predictor you want to think about. Maybe it's multiple variables, but for now, just one variable. The outcomes are alive, dead from natural causes, dead from non-cancer, non-leukemia cancer, and dead from leukemia. So it's a 3x4 table in this case. And we want to think about a bunch of nested models. So let's draw it like this. So the first table that we're interested in is this one. So this is a 3x2 table. And that corresponds to this first population. So this is sort of table 1, either alive or dead. So this is the dead cell, giant cell. And then we have however many predictors we have. Right? In this case, 3. This is 3x2. And then inside that table, inside the one part of that table, we make another split into natural and cancer. So let's call this split 2. And that's nested, so that's natural cancer. And then inside cancer, we make a final split. So this is 1, 2, 3. And so this third one splits into leukemia and non-leukemia. And we get a separate logistic regression for each of these tables. So there are 3 separate logistic regressions. Each one has a different data set. Each one has a smaller n than the previous one. Right? The next model we looked at was the baseline category. So the baseline category, if we look at this same table, is just going to compare alive with natural, alive with non-leukemia, and alive with leukemia. And there are 2 formulations of that. One is, so we put the baseline usually on the bottom, is this way, X transpose beta natural. So beta natural is a vector of parameters, including usually, so when we write x like this, we usually mean the vector 1. So what would this vector be for the predictor variable? 1, and then we have a choice. Either we could make it 1 sort of ordinally coded variable or 2 dummy variables. So let's. No. I'm saying like this here. Hold on. X is a random vector 1, something for medium, and something for high. Say, so I have 2 dummy variables, and I have an intercept. So the beta has 3 coefficients, right? An intercept, something for medium, something for high, and there's a beta for each of these guys. Log P non leukemia P alive, and log P leak, P alive. So this is X transpose beta, let's call it non, and this X transpose beta leukemia. And the degrees of freedom is the degrees of freedom of the, is the number of parameters. I want to stop for a moment to talk about degrees of freedom in these models, because I've had a couple of questions in office hours and such about that. So let's return to that alligators example, because it's a little bit more complicated, and hopefully it will show all the issues. So we have a 5 by 4 by 2 by 2 table. This is our Y, our 5 food choices. And these are our predictors. And we have 16 kind of patterns or cases, each of which have perhaps a multinomial distribution. And you can always sort of reduce the situation to a two-way table. At least it helps usually to do that conceptually when we're doing logistic regression, the thing that's predicted versus all the predictors. So it's a bit like having this, but instead of having only 3 rows, I have 16 rows. So it's kind of a flattening of the table. And the way you want to think about such a table is we get 16 patterns, means we get 16 conditional distributions. Each has 5 outcomes. I have a probability distribution with 5 outcomes. I have 4 degrees of freedom, because they have 5 probabilities, have to sum to 1, right? So like, say we have case I of 16. Maybe that's some combination of these 3 variables. We have probability of fish given I plus probability of reptile given I plus probability of invertebrate given I plus probability of, well, I don't remember what the other one is, bird given I plus probability of other given I, and those sum to 1. So we only have 4 free parameters, 4 degrees of freedom in the row. And so we have 16 times 4 equals 64 parameters for the saturated model. Now, if this was earlier in the class and I was talking not about the logistic model, but the multinomial model, the free multinomial model, the saturated model would have more degrees of freedom. We'd still use the word saturated, but because we're thinking of the whole table, a model for the whole table instead of a model for the logistic regression, what we meant by saturated would be different. Right? So this is the saturated model, and really this is the conditional or logistic regression model. What's special about this model is that we don't care about the marginal distribution of the predictors. Right? So we don't care about how much, what the probability of lake by size by gender is. Right? We're punting on that, or maybe our data collection procedure tried to collect equal numbers of each of these or something. So that's not something we're interested in. The saturated model for the full joint multinomial distribution would have how many degrees of freedom? Oh, the model degrees of freedom. Remember, I like to distinguish between model degrees of freedom, how many parameters I need to estimate the model, test degrees of freedom. Usually that's the difference of two models, and most commonly the difference between the saturated model and the model that we're interested in checking its goodness of fit. So these two things are different. 79. Okay, because if there are 80 entries in the table, they're all probabilities, they all have to sum to 1. So 80 minus 1 is 79. So these things are both called saturated models, but they're different models. One is a conditional model with 64 parameters. One is a joint model with 79 parameters. So then let's think about what's interesting. So if we were doing a model, if we were doing a G-squared test or goodness of fit test for a model inside of the saturated model, we'd be using this degrees of freedom as the model degrees of freedom for the saturated. If we're doing it for logistic regression, we use this as the saturated model. And the difference is whether or not we care about the marginal distribution, essentially, of the predictors themselves. The other thing we could think about is kind of in the other direction, what's the simplest model that makes sense? And that's something that we look at in this section and in the homework. So again, the simplest model, I mean, there's sort of depends on your point of view or what you're interested in. So I don't know, maybe in the joint case, maybe the simplest model would be everything is equal probability. That's kind of a stupid model, but it's simple, to be sure. Or an independence model is a little bit less crazy, right? In this one, what would the independence model, if we had a saturated, if we started with a full joint, and we took an independence log linear model, and we asked for the logistic regression that corresponds to the independence model as the simplest choice, what would that model be? So for the joint thing, right, the simplest model, if I don't choose this crazy one where everything is equal, I probably want maybe an independence model, right? So that would be like the log linear model. It would be here's food and lake and size and gender, and there's no interactions allowed. They're all independent. If I do this kind of projection operation, I forget about I don't care about the distribution on these variables. I only care about how they influence this. What simplest logistic regression model makes sense or corresponds to the independence model? What's the conditional version of the independence model here? Look at the parameters here. Okay, so this one has 4. 5 minus 1. 5 minus 1 equals 4, right? So there's 4 parameters for food. Similarly, for lake, there's 3. For size and gender, there's 1. So the independence joint model would have 9 degrees of freedom. Right? Do we use all these degrees of freedom in the simplest model for logistic regression? Okay, if I change this parameter, this is the marginal distribution. This is the parameter controlling the marginal distribution of G, right? So it would be like probability male equals 1 over 1 plus e to the, if this is an x, but it's called gamma, e to the gamma, or something like that, right? If I have a log parameter. And probability female equals 1 minus probability male, let's say, right? So as I move this parameter, the one that corresponds to gender, I'm changing the marginal distribution of gender, right? So when I'm regressing on gender, do I care about that parameter? No. Right. I don't care about that parameter. Okay, so I don't need that. How about this one? Do I need this one? I'm regressing on all of these three things. So I don't need this parameter, I don't need this parameter, don't need these parameters. So how many parameters do you expect the simplest model, the independence model for logistic regression to have? More? I think you were saying it. 5, almost. But they have to sum to 1, so 4. Okay, so this is the only one that survives. Right, all of these parameters are telling me about, under the independence model, the distribution of lake, the distribution of size, distribution of gender. But in our sampling assumption, say, maybe we chose so that we had exactly the same number of each of these categories. Right? Of the 16 categories, we could do that if we were sort of naturalists, right?
So are you assuming it doesn't intersect? Doesn't the null model have 1 degree freedom?
The null model. Well, remember we're doing a regression on. We have a polynomous regression, right? So we have a multinomial response. So you have the right idea. So my next question is, what do these 4 parameters represent?
Doesn't one represent the coefficient for fish, reptile, and bird?
Right. So the point is that these parameters are for the intercepts. They're for the joint distribution of the response. If I only had if I had a binary response, I'd have 2 minus 1 equals 1 parameter, which would be the single intercept. But these parameters are the intercepts for everything else. So in other words, the independence model, when I don't care about any of these, just gets compressed to all I care about is the intercept on the food. What is the marginal distribution of the food? Just take marginal on food, i.e. the intercepts. So this would be called the intercept in the software, and in the online notes, this would be called the intercept-only model. And so that's usually the simplest model that we would consider. Right? The only thing simpler than that is to say, well, these intercepts are maybe equal to each other, or they're all equal to the same value, a uniform distribution or something like that. So this is usually the simplest model we would consider. So if we go down, so all this does is it's allowed to fit the marginal distribution on food choices perfectly, and it says that the food choice is totally independent of the predicting variables. Doesn't look at them at all. Okay. So how many degrees of freedom are there for the goodness of fit test? Okay, so let's say I want to test the goodness of fit for intercept-only model. Right, so I compute residuals, or I compute 2 log likelihoods, one for the saturated model and one for the intercept-only model. I subtract them and I get a g-squared value or a Pearson value. How many degrees of freedom do I have for this test? So it'll be chi-squared with some number of degrees of freedom. What's that number? So it should compare the model which fits perfectly to the model that we're using. Well, that's too big because this one includes all this marginal distributions for these things, and we don't need that information. So this has too many degrees of freedom. Well, the -4 part is right. 64 minus 4. That's right. So this has 60 degrees of freedom. The saturated model, the model we're comparing it to, is the one that gives every row its very own multinomial distribution. Right? That's what it means to be saturated for a logistic regression. Every case, every one of these predicting patterns gets its own multinomial distribution. Each of which has 4 parameters, so 16 times 4 is 64. And then I subtract the number of degrees of freedom for the intercept-only model, which is the same as the number of degrees of freedom in the marginal distribution on the outcome. And if you do that, you get a g squared, corresponding g squared of 116, which has a very small p-value. So we can reject the hypothesis that the intercept-only model is all that we need, or we can conclude that we need that these things, lake, gender, and size, are at least somewhat predictive of food choice. So we put up a table for this of g squared. I want to expand that table a little bit, just to make it clear what's going on. We have a model, we have a g squared, we have a model degrees of freedom, and we have a test degrees of freedom. And this is versus saturated. So there's always the saturated model. The degrees of freedom of the saturated model is this is logistic regression. Food on the rest. Nope. The other one. Nope. Huh? For the saturated model for logistic regression. 64. How about the test degrees of freedom? 0. 64 minus 64. How about the g squared? Can you do it in your head? 0. Okay, then we have lake plus size plus lake times size. That was an example. This was the one that was problematic, so I'm not going to put it as g squared, but we could compute its degrees of freedom and its test degrees of freedom. What its degrees of freedom are? Well, let's do an easier one first. Lake plus size. Lake size. Oops, hold on. Let me put more in here. Lake plus size plus lake. Okay, so I even gave, I wrote this table up last time, right? So lake plus size. Lake, size, gender, all intercept only. Okay, let's start at the bottom. Intercept only. How many degrees of freedom? 4. And g squared I said was 116.76. What's the test degrees of freedom? 60. Okay. How about size? Okay, so size has 2 variables. Size is either small or large. So let's this is good. Figure out how to compute these things. So let's make a little table. Okay? So when we're doing a regression of size alone on food choice, we're looking at a single two-way table. Right? We're computing things from that single two-way table. What does that two-way table look like? Size is either small or large. And I have food type 1, 2, 3, 4, 5. Let's see. And let's put totals for this table. And I want to think about this table as containing, let's say, probabilities. Well, conditional probabilities, because we're doing logistic regression. So they're conditional probabilities. That means that we're conditioning on the cases, or the possible predictor patterns. There are two predictor patterns, small and large. And we're interested in estimating probability of 1 given S, probability of 2 given S, probability of food 3 given S, probability of food 4 given S, probability of food 5 given S. How many degrees of freedom do I need to freely estimate these probabilities? For this, I need 4, because they sum to 1. Have a probability of 1 given large, and so on. Do the columns sum to 1? No, right, they don't. Right, so these two things are free, right? So how many are the total degrees of freedom? 4 here and 4 here, so a total of 8. In the model degrees of freedom for size. And so what's the test degrees of freedom?
64 minus 8.
56. How about gender? We have either male or female alligators.
It's going to be 4.
Degrees of freedom, and what should be the degrees of freedom here?
4.
8 again.
Yeah.
Same as this, just instead of SL, it's MF. Okay. And this is 56. And I can fill in the numbers here. 114.7, 101.6. So you can roughly see these things are still not, remember this is the expected value of the G-squared statistic, so these are still pretty poor fits. How about lake?
4 times 3.
How many okay, so how many lakes are there?
4.
And foods?
Yeah, 4 times 60.
5. So degrees of freedom? 16. And the test degrees of freedom? 48. And if you compute the T-squared, you get 73.6. Okay, how about lake plus size? Think about that for a second. Hint, it's not this plus this. 20, why?
Because you have 3 variables for L, 1 variable for S, and intercept.
Yeah. So you could think about it as being the linear part, the linear predictor. So I have some food coefficient, intercept. Then I have my lake portion. So these are dummy variables for lake. And then I have one more for size. So 1, 2, 3, 4, 5. And then I multiply that by no, 4, yeah. So in other words, I have 4 here, 4 here, 4 here, 4 here, 4 here, 20. Or 8 for size, plus 16 for lake, minus 4 for things that I double counted. What did I double count? If I just added these, what would I have double counted? Which parameters? I heard it. The intercept, right? So it's just that this model, this degrees of freedom for this model includes the intercept. This also includes the intercept. So I have to subtract the intercept because I've double counted it. There's different ways of getting to the same answer. Okay. In some sense, in logistic regression, once you figure out how to write these linear predictor terms, you can always compute the degrees of freedom because you're just counting the number of parameters that are in the model. Like how many betas do you actually need to write it down? I didn't write. These should also have like food, right? So there's more than multiple rows. Okay. So the test degrees of freedom. (64 minus 20) 44. And the g squared here is 52.5. Lake plus size plus sex, gender, and degrees of freedom. 24. (40) is 64 minus 24, and 50.3 here. And this one is 32. Which is also 32. 64 minus 32. And this has a number, but it's not a good number because of the algorithm problems, the collinearity problems. Okay, good. So hopefully that helps clarify.
So now that we have this table, how do we figure out which is the best run? Do we have to look at like all possible ways to compare two things and then see which gives us the best delta G? Or
Yeah, I mean, there's sort of multiple philosophies for doing that. I have a little time at the end of today or next time I'll start talking about some formal methods for making those decisions. I mean, just eyeballing it, the only one that's going to come up to be a pretty good fit is sort of, well, this one.
how do you know that just by looking
Or
at
this one. I mean, I don't, but so these are the best. So, okay, so I'm looking at the ratio of g squared to the expected g squared. Everything below here is going to come out to be a small p-value or a poor fit. I didn't calculate it. You can sort of eyeball it. You can type it into your computer and ask what the p-value is, but it's going to be small. And the first time they start getting not so small is up here. And you can ask, well, okay, these two models are pretty closely related. Is it worth adding gender? That's a question we can ask that has 4 degrees of freedom, but it's only a drop of 2. And so the delta g squared between these two is only going to be 2 with 4 degrees of freedom, which won't be significant. Sort of suggests that our juice is running out here.
So which one does it say is better in that case, with gender or without?
I mean, this one will always fit better, right? But you have to make the judgment that it doesn't fit significantly better, and so it's not worth adding it in. What would be really nice is to add some other penalty function that counts the number of parameters or something like that. And so that this goes up, and then it starts to go down again once I add too many parameters that aren't doing much benefit. And at the end of today or next time, I'll talk about a function that does that. But for now, it's sort of you have to make either do the significance tests and keep going until no further jumps are significant. That's a perfectly valid way of doing it. Or you can sort of make some decision about that. I mean, this jump will show up to be significant, I think, but let's see, was it 12 versus 20? So that'll probably be just significant or so. But there's this issue with this with this giving an error, so you don't want to do that. So I would say that with this, you sort of stop maybe. And then the other thing to note about this kind of thing is, all right, well, we stop here, but we still don't really like the fit that much. If the p-value, if you plug it in, it's good enough in the sense that right, it's sort of the opposite of significance. We want the p-value to be not significant. Right, that's sort of our goal in finding something which is a good fit. But we like it better when this is like a big number, closer to 1.7 or something, right? And so this is a situation where you can kind of justify thinking about overdispersion, right? Because you've already checked adding variables, and that doesn't seem to help in terms of reducing the fit significantly. So this is a place where overdispersion might make sense as a way to kind of improve the fit or to make our confidence intervals more realistic. And you can imagine something like, oh, well, maybe this data was collected over the period of a couple months, and there was seasonality effects that don't create a Simpson's paradox, but increases the variance in food availability or something, right? So there was somehow our assumptions, the sampling assumptions were violated. And then we could estimate a scale parameter, which is just the ratio of these numbers, except you don't want to use g squared. But conceptually, it's the ratio of these numbers. We're going to force them to be 1 by introducing a new parameter, which is just this. You have to use Pearson because, well, for sort of technical reasons, basically. That Pearson gives you a good estimator. Likelihood doesn't give you a well-behaved estimator. It has bias in it or something. So you can estimate an overdispersion parameter, which essentially forces the goal of that thing, although it won't be literally true because we're not using g squared, we're using x squared. The goal of that is to force this ratio to be 1, and therefore make it right on the median. And what that will do is to this sigma squared, which is 1.148 squared, will increase confidence intervals, standard errors of the beta, and change the significance of our tests. So it reflects that it's a way of in some ways it's a conservative assumption because it's a way of reflecting that your model didn't work as well as you hoped that it would. Okay. So let's look back now at some of the other techniques for the other choices that we had for yeah.
So we do this table and you see that our p-value is pretty high. That's, and we construct this overdispersion parameter.
So the overdispersion parameter here is because the p-value is sort of small.
Sorry.
Yeah, I know. So it's significant, but the fit is not quite as good as we might like, and we can tell ourselves a story about why.
So that would give us like better confidence intervals.
Right. So in other words, if we fit this without this parameter, we would get beta birds. I don't know, whatever size, right? Birds large, right? Which would be some number. And if we estimate this, it will make the confidence interval a little bit larger. That's and it'll be harder to get significance for these. That's sort of the main effect for it for our purposes. It's just it sort of reflects the fact that we're not as confident in our estimates because the model didn't fit as tightly as we would have liked. Okay, so to return to the cancer example, we have 1, 2, 3, 4 categories. And we want to build a model now, and instead of being based on the baseline, is based on this adjacent category idea. That is what we're going to use as our linear predictor, is something like probability of alive given probability of died from natural causes, which is number 2. This is alive. This is non-leukemia, and this is leukemia. So 2, 3, and 4 all have died, and 1 is not. Log P. So now we're comparing adjacent categories instead of a baseline versus P non, and log P non divided by P leukemia, and all of these will be some X transpose beta, and the beta is a vector that depends on alive, X transpose beta natural, and X transpose beta non. And writing that out, we have some intercept, alpha 1, alpha 2, alpha 3, plus we have only 3 intercept terms, the number of outcomes minus 1. And so the intercept-only model would be done. And then we have a beta alive M, for dummy variable for M, beta, let's call this beta natural M, dummy variable for M, beta non M, dummy variable for M, beta alive high, so this is supposed to be radiation exposure, dummy variable for H, beta natural H, dummy variable for H, and beta non-leukemia H, dummy variable for H. So that would be our full model. At this point, it's equivalent to the baseline category model until we make a decision to set these equal by forgetting about that and forgetting about that. So in other words, we set these betas equal and these betas equal. Now we're taking in a particular view. What's the view we're taking? We're saying that if I have LM 1, 2, I have this 2 by 2 table. The odds ratio that I get for that will be equal to the odds ratio I get from the table LM23 will be equal to the odds ratio I get for LM34. And I guess I want to say MH? No. Say LH 1, 2. The theta for that equals the theta for LH 2, 3 equals the theta for LH 3, 4. So that's what we're saying when we set those things equal. We're saying that some of these 2 by 2 odds ratios that we could use to describe the full dependent structure are assumed to be equal. And as usual, we can count for the degrees of freedom. We just count the number of parameters. So before I set anything equal, I have 9. After I set them equal, I have 1, 2, 3, 4, 5 degrees of freedom. 5 model degrees of freedom. I would compare that to a saturated model for my test degrees of freedom. So then we have a different model entirely, which is this proportional odds cumulative logit model. We start with the same table, LMH. 1, 2, 3, 4. Now this one doesn't make as much sense for this particular example, so just think of this as 1, 2, 3, 4, 4 possible outcomes if you want. Though of course we can still state it, but it makes most sense when there's like a really strong ordinal structure, just like this does, right? You could sort of think about this as being ordinal, but I don't know, maybe it's not. Anyway, so this says it's kind of like halfway between the adjacent category and the first one, the partition. So this is an overlapping partition. That is, we have 1, 2, 3, 4, and the odds ratios that we're interested in. Compare 1 against everything else, 1 and 2 against 3 and 4, and 1, 2, 3 against 4. So it's not equivalent to any of the previous 3 models. And our equations will be log p alive given p nat plus p non plus p luke is equal to some alpha 1 plus beta alive. These are different betas, of course. Beta alive high, dummy variable for high, log p alive plus p nat divided by p non plus p leukemia is alpha 2 plus beta an for alive and natural, m times the dummy variable for m plus beta an for alive and natural, dummy variable h, dummy variable h. And then the last one is log p alive plus p natural death plus p non-leukemia divided by p leukemia as a function of an alpha 3 plus beta alive natural non, comma m, dummy variable for m plus beta an n h, dummy variable for h. Okay. At this point, we still have all of our degrees of freedom, right? We've just done another parameterization for our 9 degrees of freedom. And then we set these equal, this one equal to that one, and this one equal to that one. These two equal and equal to that. And once we've done that, we have, so setting those equals defines this thing, the proportional odds cumulative logit model. And what we're saying in terms of odds ratios of 2 by 2 tables. We're saying that the theta for, say, low and medium, that's 1 versus 2, 3, 4, is the theta for low versus medium, 1, 2 versus 3, 4, equals the theta for low versus medium, 1, 2, 3 versus 4, And similarly, if I replace M with H. Yeah.
When you state the assumption for us to set this three theta equal to, I was wondering what is the assumption for us to set up those three theta to each other.
Right, so that's this thing, this choice, this assumption, is what we call the proportional odds cumulative logic model. That's the definition of the model, that we make that assumption. And
So what is the motivation for us?
well, it's that you think all these odds ratios should be the same. I mean, it's a way of representing the ordinal structure of the data and reducing the number of parameters. It's a hypothesis about the way that things are related.
How that is why in the degree of freedom, I was thinking about 56, right? Because the reason why I was 56, I using the 2 times 3, got 6. I was wondering how
I'm just counting the parameters. There are 3 parameters for alpha, and after I set things equal, there are 2 parameters for beta. So it's also true here that there are 5 model degrees of freedom. And one of the ways that this model arises is this PO LC model. Can arise in the sense that the assumption can be justified by a discretized continuous response. So if in fact we have a relationship like z equals some coefficient plus gamma 1 x1 plus gamma 2 x2 and so on, and then I have an error term, and this error term is not quite normal, but this other distribution, logistic, it also has like a bell curve. And then we've sliced, this is so this is like, it's not a normal variate, but it's a continuous variate. And then we've sliced this up into regions by some cut points that don't have to be equally spaced. So the picture is X, or linear predictor, I guess. So this quantity. Let's call this capital lambda. And here we have our response. And so we have some sort of like nice regression, elliptical thing. And then our response variable just got cut, not by us, but by nature, into some categories. So these are the data points. Instead of seeing the z value of data points, we just see, oh, it was in category 0, category 1, category 2, category 3, category 4. So if these all got compressed, then this will be the correct model, or it will satisfy this assumption of equal things.
Yes, I was wondering, is that a confidence interval for the parameters, space? Is that a confidence?
No, it's not a confidence interval. It's saying if you started out with a continuous variable, but all you were able to measure, so for example, like the cholesterol study. So cholesterol is a continuous variable, but you were only able to measure ranges, say, right? Because of the limitations of your experimental procedure. And if the noise, if the distribution would have looked roughly elliptical if you had access to the full data, then this is a good assumption, this proportional odds cumulative logic. So the answer to your question is, that's one way that you can justify it. And there's this, there's a thing on the online notes about an ice cream study that sort of gets into some more detail about this stuff. So you should check that out. So I'm going to change gears for the last 10 minutes or so and talk a little bit about more careful procedures for choosing which model to use. So if you have one of these analysis of variance tables, analysis of deviance tables, that tells you which model increases are significant, which are not, how should you think about the problem of picking a good model? So this is a huge topic. I mean, there are probably hundreds, if not thousands, of papers written about it every year, and it's very complicated. But let's talk about the basic idea. So you can think about it as it's a trade-off. Right? It's a trade-off between, on the one hand, something which is a little bit like a sensitivity. That is, we have enough parameters or enough freedom in our model, enough choice in our model to capture the relationship. And to keep the bias low. As if I have too few parameters, my result is going to be very biased. Like if I had no parameters, I always choose a uniform distribution. My guess is very low, very biased, right? It doesn't take into account the data at all. As if I add some parameters but not enough parameters, I've kind of shrunk it toward my model. Right? I've biased it. So suppose I take an independence model, no matter how far away from the independence model is, I've always chosen a point on the independence model. So it's a very biased estimate of what's going on. And on the other hand, we have kind of a specificity kind of thing. And that is, we don't want to overfit or find spurious relationships. Right? If we include all the variables, if we include a saturated model, we'll always fit perfectly. But when we look at a data point that wasn't in our data set, it'll be garbage. Right? The prediction won't be very good because we effectively just looked at each data point. So in other words, this is usually called the bias-variance trade-off. So this you could think about as having high variance or avoiding high variance. So predictions that I could make, if they have too few parameters, I get high bias or underfit. Right? I get a model that has more to do with my assumptions about which parameters were zero than it does about the data. Right? It's pulled toward a very narrow view of the world, very biased view. If I have too many parameters, then I get high variance in the sense that if I draw, if I have a big data set and I draw two different subsets of that data and I fit my model, I'll get two completely different answers. Right? So the model will change too much based on the specific observations it sees. So it fails to see kind of the common structure. High variance in my estimators. The bias and the variance are in the betas. You can think about that. They're in the estimators. It's overfit.
Yeah, excuse me.
Yeah.
So I was wondering, so here we're using the bias law, whether we are refer to, say, the expectation of the estimate parameter is equal to the expectation of the true value.
Right.
But the variance of the expected estimate
Of these
beta
parameters.
is greater than the
Right.
variance.
So we're saying we use too many parameters, our betas will have too high variance, they'll jump around too much. If we use too few, like if we zero them out, they'll have high bias, right? Any parameter that's been zeroed out will be always very biased to be zero.
Okay, we're just talking about so how about the expectation of the estimate do you think, I was wondering, so bias here, whether we are referring to the expectation of a.
Yeah, whether the expectation of the beta is the true beta.
For the variable.
All right, so that, if we saturate a model, we'll have no bias, but it's not a very good model, right? In the very long run, it will always converge, but in the short run of actual amount of data, it won't give you an accurate estimate, for example. Okay, so the idea of a good model picks a happy medium between these. It's a good trade-off of fit versus complexity. A picture in your mind is something like number of parameters some value, and bias, maybe you have two axes here. Bias is going down, variance is going up, and you want to be here. Right? You want to have some sort of happy trade-off between the two. And a nice way to think about that is what happens when you take your model, which was fit or trained on some data, and you use it on data that you've held out. So in your next homework, you do this, you hold out a small amount of data, and you check your model. And so cross-validation is the name of that. And the idea is that you want to choose a model which performs well on data you haven't seen before. Right? You can do that in a practical way, or in an experimental way, by just holding data out and trying different models. And that's this cross-validation procedure, but you can also do some theoretical things for that. Another schematic picture. Think about model complexity as going from low to high. And I have sort of prediction error. And I draw two lines, one for the training sample, the data that I fit my model on. It's going to look like this. Right? The more complexity I add, the lower the error is until I get to the saturated model, and it's 0. There's no error because it fits exactly. And if I have some data that's out of sample, like a test sample, the idea is that it should look more like this. At first, there's a payoff to complexity in terms of my error on the test sample. And then as I increase my complexity, at some point, the variance takes over, and my fit becomes worse. My prediction error becomes worse. And so what we'd like is an idea for finding or approximating that sweet spot. The idea we've been using so far is keep increasing complexity until you run out of significance, and then stop. It's a perfectly valid idea, but there are lots of other ideas about how to do it. So a common way to do this is to break the problem into two parts. One, assign a score, often just a number, to measure model quality and balance these two concerns. Sort of a utility function. Of course, there could be dominated models. There could be models which are worse on both things, and you should throw those out. Right? And then second, search over the model space. For the model with the best score. Now in this class, for the most part, number 2 is easy because we're using examples with fairly small numbers of models, right? We only have 9 models or 10 models or 20 models. But if you have a lot of variables, of course, this number of hierarchical models grows exponentially. And so for many, many variables, this problem becomes very, very difficult. It's this search problem. So together, these problems are something that's called an NP-hard problem for general models. So difficult in a formal sense. So let's now think just a little bit about what this 1 could look like. So as we sort of go up the hierarchy, so if we think about a graphical model, some variables, A, B, and C. So independence model, right? That's contained in some model where I'm allowed to have an association between A and C, but they're independent of B, and that's contained in a model. Let's draw an arrow. I'm confusing arrows, right? And that's contained in a conditional independence model, and that's contained in a homogeneous association model and contained in, say, a saturated model. Right? So each of these are bigger models. At each point, I add more parameters. And the likelihood, which is sort of my naive measure of how well it fits, the likelihood always increases until it's as good as it can get at the saturated model. Right? Or the fit keeps improving. We keep moving in this direction. The prediction error of the training set goes to 0. And so one simple way to fix this or penalize the complexity is to adjust the likelihood itself so that it'll eventually decrease. Right? So the likelihood is going up, up, up as I add complexity. Let's add some other penalty function so that makes it go down when the complexity gets too big. Okay. So the idea is you take, OK, we have a log likelihood. I have theta star as my maximized parameters and my estimated parameters. The fit model, given the data. And that's what we would normally use for maximum likelihood estimation. And then we add to that, or subtract from that, an additional term, f of n g of p, where f is a non-decreasing function of sample size, and g is a non-decreasing function. And of course, there are more complicated ways of doing this, but this leads to some good ideas. A non-decreasing function of the number of parameters. So this function now will go up by likelihood and will go down by complexity. And so we'll automatically choose a trade-off point, a model which optimizes this total. And the most popular choices are fairly simple versions of that function. There's the Akaki information criterion, AIC, which is just the likelihood minus the number of parameters. And then there's the Bayesian information criterion, which is the likelihood minus the number of parameters divided by 2 times the log of the sample size. And there's another criteria, which I won't write out right now, called the widely applicable information criterion. This exists because the theoretical justification of these things behaves poorly at certain points in the model. Just like when we go to the boundaries of the model, all bets are off. When all bets are off, you have to use a more complicated justification. So I think I'm out of time. I'll stop here, but maybe next time we'll talk about where these come from or why these two functions, how these two functions particularly can be justified.